Hello, and welcome to the video lecture number 16 on the topic of power in section 5.7. All right, of Survey 11th edition. All right, so a pretty single topic lecture here. We're just going to discuss power. Also a fairly straightforward idea, I think. I think you'll find this idea pretty straightforward. Let's get into it. All right, so first of all, a word you've probably seen a few times, watt, right? Think wattage. So what is a watt? It is the unit of power. All right, and so it's represented by a W. It's a joule per second, okay, or a kilogram meter squared per second cubed in base units. All right, and importantly, power is energy per time, right? We define watt before we define power, all right, but it's, in a sense, watt is a more everyday word, right? At least the technical definition of watt and the technical definition of power, we know watt more. But anyway, right, so it's just energy per time. All right, and last thing, the dimensions of a watt are mass, length squared, times the -3, right? And that's just, we can see matches up the base units. Okay, so that's it. We're just talking about power here, right? Energy per time. All right, so a couple ways to think about power. We have average power, right? So that's P with a bar above it. And that is work per time, okay? But then I said power is energy per time, but of course work and energy are the same thing, okay? Work, remember, right, creates energy. Energy by definition is, potential energy at least, is something that has the capability of doing work, right? We know there's a direct relationship between kinetic energy and work, so you can't have one without the other. Now, depending on the context of the problem, the question that's being asked, sometimes you actually might want to think of the numerator here as change in energy more generally, all right? Okay, but if we are thinking in terms of work, then we can be specific about where the work comes from a particular force, all right? And that's relevant too, because if we're talking about a situation, especially a mechanical situation, you'll see that when we talk about power, we tend to do it with the same specificity that we do with work. What I mean by that is that it's the power of a particular force. So what's the power output of gravity? What is the power output of friction? What is the power consumption of friction, for that matter? So that's it. It's always specific to a force. So it makes sense then to focus on work and then to focus on the force that's associated with that work, acting over some distance. And of course, theta is the angle between the force and distance vectors. Okay? We can also talk about instantaneous power, okay? And not in the calculus sense, just kind of in a sort of different approach sense. And in that case, it becomes force times velocity times the angle between the force vector and the velocity vector. Now, where does that formula come from? Well, it actually just comes directly from above, because if we rewrite it, we see that the distance over time, well, right, as I put in parentheses here, that's the definition of velocity, isn't it? All right, especially if it's a very small distance over a very small time, then it becomes instantaneous velocity, or approximation of instantaneous velocity. Okay, so that's it, right? So kind of two different approaches depending on what's being asked, right? And two types of power, basically though, two types of problems. Ones that ask about average power and ones that talk about instantaneous power, okay? So let's look at example one. International Space Station, right? Up here at an altitude of 435 kilometers above the surface of the Earth, all right? Give or take a few dozen kilometers, right? Give you the mass of Earth, the radius of Earth, right? Seems like we're asking a question where we have to do a lot of calculations. Well, not actually, right? So based on the orbital speed we find for the International Space Station, ISS, what is the power required to keep it in motion, right? Well, the work required is equal to the work of gravity. So first of all, right, and that's the thing, right? That's the only force acting on the International Space Station. We can agree, right? So then we have the power required, therefore, must be equal to the power of gravity. And the power of gravity, as we know from our definition up here, is the work of gravity over time. But the work of gravity, defined by the force of gravity, times some path, right? Times cosine of the angle between the force vector and the path vector. And here I'm using S because S is the typical letter for arc length, right? Well, here's the thing. It's 90 degrees. Why is that? Well, think about it, right? Here's the orbital path, S, right? A circular path. And the force of gravity always points towards the center. Well, then it's always 90 degrees between the instantaneous velocity vector and the d vector, right? The path vector. All right, so that's telling us what? Well, it's telling us then that the work of gravity is 0. Therefore, the power to keep the International Space Station is 0 watts. It's free. It takes no power there, and no work is required there is no power required. All right, it's 0 watts. It better be, because how could the International Space Station have enough fuel if it did cost power, right? Okay. Now the space station is just following around Earth. Okay. So a volcano spews 450 kilogram rocks. Okay. So it looks like we're talking about the power output of a volcano. It spews them vertically to a height of 320 meters, so they're shooting straight up in the air. If the volcano spews about 1,100 of these rocks every minute, okay, so this is a pretty violent eruption, estimate the volcano's average power output. Okay, we need that. Okay, so we're just going to find the energy of each rock, and the energy of each rock, and that's the energy that the volcano puts into each rock, has to be equal to the final potential energy of the rock. All right, and that's assuming no air resistance, because in order, because there had to be enough energy to get up to that height. So the final potential energy of the rock is equal to the energy input into that rock, and that's 450 times 9.8 times the height of 320, and that is 1.411 million joules. Okay, 10 to the 6. Okay, but there's more than one of those rocks, so the total output is just N times the energy of each rock, all right? And that gives us 1.55 billion joules, right, because it's 10 to the 9. And then we're just going to take that 1.5 approximately billion joules and divide it by 60 seconds, number of seconds in the minute, to get our average power output of the volcano. And we get 2.59 times 10 to the 7 watts, or 25.9 megawatts, which is to say 25.9 million watts. Okay? And yeah, it's pretty realistic for a violent eruption. Of course, it would be harder to count it. It's not like volcanoes just pump out rocks, right? Nice, equally sized rocks. There's gas and a lot of pressure considerations, vibrational energy, right? But in terms of total energy output, sure. All right? Energy per time, power. Okay. A couple more, all right? So bring it back down from exciting things like orbits and volcanoes to just cars and boxes, all right? So a 1,500 kilogram car traveling on flat ground at 18 meters per second, oh, we've seen that before, slams on its brakes, and the friction between its tires and the road caused the car to come to a complete stop over a distance of 100 meters. What was the power expenditure of friction? Okay, so here's our picture. We have our kind of our energy states here, right? Initial velocity, 0 final velocity, distance, okay, and then the force of d, I guess, just for the force to decrease, I guess, the variable there. It's not, maybe it's drag, I don't know. All right, it's more like the force of friction. Not sure why I put a d. All right, we know from before that friction does a work of friction, okay, and that's going to be equal to change of kinetic energy. This is just basically the work energy theorem. So there we go. That's the work of friction. 240,000 joules, negative 240,000 joules, okay? And time, so that's the thing, right? So we can definitely answer the energy question with just the work energy principle, or we could use conservation of energy with non-conservative force, and saw that in the very last lecture, okay, example 1. Here's the thing though, we can't, since there's power, and power has a time in it, we have to do something else. We have to find a time. And that's interesting. I'll say right now, and I could have put this in as a concept question. Think about a spring, right? A spring is a non-constant acceleration. We never talk about how long it takes the spring to compress because we can't go back to kinematics. There's no way to find the time that the spring compresses because we don't know its acceleration. We don't know the form of its acceleration, all right? Even if we were doing calculus, it turns out the form of the acceleration isn't just some higher order polynomial. It's quite complicated, okay? And so here's the thing. So what can we talk about? We can't talk about springs in terms of power. You'll never see a question that says, what's the average power output of a spring? What's, how much power, what was the average power consumption of the spring or anything like that? We just don't have the tools to do it, okay? So, but here, friction we definitely can because friction is going to be a constant acceleration, all right? But it will require kinematics because time is involved, all right? So there we go. We got a kinematic equation, okay? That's going to give us A. So I go ahead and solve for acceleration, and there's our rate of acceleration, okay? And then I'm just going to use that rate of acceleration to find time. I kind of did this the long way. And you get 11.1 seconds, right? That's the total time for it to stop. It's 100 meters, about 300 feet, right? Friction, friction's doing the work the whole time. Now, I could solve for the friction coefficient at this point, right? I have enough information, but we weren't asked for it, so we're not going to use it. But we definitely are not going to find it, that is. But we definitely needed the time, and we got it. So we can just plug that in. We'll take our work of friction and our time, and we're going to find then the power of friction. It'll be a negative value because we got to think of it because it's taking power away from the car as opposed to putting power into the car, and the car was the focus of the energy. Okay, thus negative power. All right, so it's removing energy at a certain rate, at a rate of 22,000 watts. All right, last one. Okay, this one has both instantaneous and average power. Okay, so a box is pushed from rest with an angled force across a frictionless floor. All right, we'd have a flutter free body diagram if we made it friction, right? That'd be a good one. And angle is negative 25 degrees, or 25 degrees below the horizontal. And the magnitude of the force is 50 newtons. Right, so the mass of the box, we know 35 kilograms. How much work is done to push the box a distance of 20 meters? All right, well, we've done that before. Now something new, or that's relevant to this lecture. What is the average power input in pushing the box those 21 meters? Okay, good. And then what is the instantaneous power at a particular time, specifically 5.6 seconds? Okay, all right, so we definitely going to be some kinematics involved in both B and C. Let's do it. Okay, so first step, just going to find the work of pushing. Okay, that's just going to be the force of pushing and the distance. All right, taking the vectors together. Kind of ignore that step. Care about this one, right? Because we know that the definition of work is 50 times 21 times cosine of the angle between the two. That's what this is telling us, but I accidentally showed you something that you're not supposed to see, which is the dot product. Okay, but anyway, this we know is just because this is just force times distance times cosine of the angle between the two. Okay, and there we have the 952 Newton meters. Okay, good. We just found our work. Okay, and I put in units of Newton meters as opposed to joules. Okay, so then our average power output, and by the way, that would be the answer to part A. All right, and the average power output, which was review. So the average power output of the work of pushing over the time will just be the value that we found there. All right, over the time. Right, I put as delta t, but the clock started at t equals 0, so we're fine there. All right, and we just need to find the time. All right, well, what do we got? So we know that we're going to go 21 meters. So we know our x. Okay, and C, we know the acceleration if we set up the right equation to do so. All right, and so there we have the acceleration is just the x component of the pushing force over mass. How do we know that? Well, just think about the free body diagram here, right? We weren't asked for the normal force or anything, because the normal force would be affected by the y component of the pushing force, right? But we only care about this component of the pushing force, which is just Fx, which is just going to be F cosine theta. Simple as that, because that's it. That's the only force. Again, friction free, right? Rather simple free body diagram. So that's all that is right there. That's Newton's second law, right? And then that x component, as I said, is F cosine theta. Okay, so, and then, right, there's our equation, just rewriting this, right, specific to this problem and this figure. And solve for t. All right, t then is the square root of 2dm over F cosine theta. Plug in the values. Oh, not yet. What I'll do is I forgot to do that. I will substitute this back in symbolically right into that equation, okay? Because it's just t after all, right? All right, and then we already know the form of the pushing force, which was Fd cosine theta, definition of work, okay? And that would be that would not be the form of the pushing force, but the form of the pushing work, or the work done by pushing. And there's our average power output, okay? And it's average because we have a big D here, right? We don't have a distance if we're taking it instantaneous, and you'll see that in part C. That's what's good about this problem. It really compares the difference, kind of practically speaking, between average power problems and instantaneous power problems. Okay, so we'll clean that up. I took the cosine theta ends up being up to the 3/2 power, which is pretty cool. All right, or you could put it inside a square root and raise it and cube it. Either way, you'll get the same result. All right, and then that's what's left over inside the square root. Plug in all our values. Okay, 25 degrees, 50 newtons. Yep. All right, this is our. It's hard to read, but this actually says 21 meters, even though it kind of looks like 2 centimeters. And that's 2 times 35 kilograms. So those are our numbers, and we get 167 watts. That's the average power output. Okay, so good thing here. Let's think about this. I'll before we segue to part C. What's the instantaneous power output at the moment the person starts pushing? Okay, well, we know instantaneous power output is P equals FV cosine theta. Okay, so what does that tell us? Is the instantaneous power output at the moment the person's pushing. Starts pushing, that is. 0, right? Why, right? So P naught is 0 because V naught is 0. Because the box is accelerating, right? But it's accelerating from rest, like so many of our systems. So then the final power output is going to be rather large, right? So the final power output, right, at the minute we get to our 21 meters, because that's how long we've been pushing, and however long that took. We never found the time, but we could solve this and find out how many seconds it is. Okay. But the point is that would be maximum, because then it's going fastest. So this average is just halfway between the two. Why is that? Because the velocity is increasing linearly, isn't it? Think about it. Here's velocity, here's time. The velocity is increasing at a linear rate because the acceleration is constant, because the force is constant. So that means whatever is the instantaneous power output at the end and instantaneous power output at the beginning, well, the average is just going to be P final minus P initial divided by 2. Right? Linear. Okay? So that's pretty cool. You could actually find it that way. There'd be no need to, but that's what that 167 represents. Just the average of the final power output and the 0 instantaneous power output. All right? So that means actually it has to be exactly half of the final. Okay, now let's do part C. Okay, so part C, I'm going to find the time it takes, let's see, what is instantaneous power at, so actually I'm going to find V at 5.6 is what I'm going to do. All right, so notice the kinematic equation I'm using. I'm not using this one. I'm using this one, right? V naught plus AT. Okay, that's this. Okay, A is still written in terms of Newton's second law. I never found a number, I just left it symbolic. Okay, so then if I want the instantaneous power output at that moment, so I'm really big on leaving everything symbolic for this problem. All right, well then I'm going to have force, that's just a value. All right, in fact that's going to be let's see, because that's the total force, this is the total velocity, this is the time, which we were given, 5.6 seconds, and this is the angle between that force vector and that velocity vector, okay? And so that's why this isn't fx, it's f, because then when I take the cosine theta, then it becomes fx effectively, because after all, that's what work is all about. It's taking the component of the force that's parallel, okay? And that's the parallel is obviously the x component, okay? Parallel to d, that is. Okay, so hopefully that makes sense, right? Again, this is after all just just rewriting this. Oh, and don't again, this notation I should have removed it. It should just be like this, right? You don't need to know that it's this thing called the dot product. It's not complicated, but it's just not relevant to the class. We just skip right to the definition here, okay? In this class. All right, and then this cleans up nicely. All right, the cosines come together, the f's come together. Okay, what do I get? 329. Oh, look at that. That's times 2. Why is that? Well, if you actually solve for this time, it's about 5.6 seconds. So I was actually asking, I was being a little secretive about it, for the power output at the end of the 21 meter push. Because it takes this long to push it that far with this particular acceleration. Okay? So you can see how they're all related, all right? And that's why this value is twice that one. Okay? Because this is the average, that's the final. And the initial is what? 0 watts. Okay, so this is a good problem to end on, I hope. I think it was an interesting one. And thank you so much for watching this lecture on power.